It's lovely to see such a great audience, quite a lot of you, and I think there will be more people joining us. We have about 60 registrants, so that's fantastic to see. So a very warm welcome to you to our second Friends of the Bodleian Lunchtime Lecture of this academic year. My name is Virginia Yadowisan. I'm Head of Conservation and Collection Care of the Bodleian Libraries, but most importantly today, I'm the Secretary of the Friends of the Bodleian, and it is my pleasure to introduce you to this lecture today. What it means to be the Secretary is that I largely curate the lunchtime lecture program for the Friends of the Bodleian, of which we have 6 every year, and we advertise it as widely as we can. So we like to keep our program very varied for you, for our public, and I thought we ought to offer an event for those who enjoy the history of mathematics. And here I must be very thankful and express my thanks to my friend Professor Nigel Hitchin, who's sitting here with us today, for introducing me to Professor Jeremy Gray, who's our guest speaker, a fabulous guest speaker today. Professor Gray studied mathematics at Oxford and has a PhD from the University of Warwick. He's now an Emeritus Professor of the Open University and Honorary Professor in the Mathematics Institute at the University of Warwick also. His research interests are in the history of mathematics from the 17th to the early 20th centuries, especially geometry, mathematical modernism, and its links with the history of mathematical logic, as well as the philosophy of mathematics. In 2009, he was awarded the Albert Leon Whiteman Memorial Prize of the American Mathematical Society for his international contributions to the study of the history of modern mathematics. And in 2016, he won the Otto Neugebauer Prize of the European Mathematical Society for his work of the history of mathematics. In 2012, he was elected an inaugural Fellow of the American Mathematical Society, and he's also the author, on top of all of that, that wasn't enough, he's also the author of 14 books. For example, Plato's Ghost, The Modernist Transformation of Mathematics, and Henri Poincaré, A Scientific Biography. Professor Gray tells me that what's most likely to stop him working is his new grandson. But before that, we kidnapped him, almost. And we made him work very hard with us, and through, a few months already, by coming to us, looking at our collections here in the Bodleian with our curator, Sarah Wheel, curator of rare books, and other colleagues who've been helping Professor Gray to prepare this lecture, Euclid in Parallel, he's bringing to you today. So Professor Gray will also be showing us a selection of items that we've put on display for you. So you, at the end of the lecture, you're very welcome to come closer and take a look. This is quite rare, display of books, not with a glass in between to interfere with the direct experience. But without further ado, I'm giving you Professor Gray, and please help me welcoming him.
Well, thank you for that nice introduction, very nice invitation, and thank you, Nigel, for helping to bring it about. So I wanted to take the opportunity to talk about some of the very lovely books that are in the possession of the Bodleian, which is why you're here, among our editions of Euclid's Elements. And of course, this is a book that's existed in very many editions. It's been an important part of the intellectual and practical culture in ancient times, in the Islamic world, and in the modern world until recently. And it's a remarkably careful account of geometry. It's often held up as an example of complete rigor, which it isn't, but several mathematicians knew that it was not exactly completely rigorous. Fewer philosophers, I have to say. There is a problem, quite a few little problems with Euclid that are substantial, and that's the story here that I want to tell about what's problematic about it and who knew. And the problematic bit starts with what you see here, which is a picture of 2 lines crossed by a third. So, it should work. So there's a red line, there's a blue line, it's crossed by a third line. This configuration will turn up in various orientations. As you can see, there are 2 angles here, alpha beta. And the parallel postulate says that if the angles alpha and beta add up to two right angles, to less than two right angles, then the red and the blue lines meet where you think they're going to meet, somewhere over there, right? It doesn't say actually anything about parallels, but it does imply that if alpha plus beta is equal to two right angles, then you would have parallel lines. And this is a page from the 888 edition of Euclid's Elements, wonderfully digitized by the Clay Foundation. We're all very grateful for that. And what you don't really see here, so I'm going to blow it up and show you in more detail, is a little picture, which is the theme of our talk, and there indeed you see some parallel lines. But the little picture is a kind of thread through this talk. It's a very strange picture. It has really two lines that ought to be parallel, but somehow something funny happens. So it's kind of icon, really. But it actually tells you that you're looking at the first book of Euclid's Elements, Theorem 27, so that means 26 theorems have happened already without any talk about this axiom. And it says that if you have this axiom and the indicated angles are equal, A equals B in this case, then the red line and the blue line are parallel, right? So that's what the purpose of the parallel postulate, as it's called, is to establish the existence of parallel lines that have not been at all talked about by Euclid before. So the good news is that if you have a line in the plane and a point P not on this line L, then there's a unique line through P parallel to L. So if I draw a line on the ground through my feet, and I take the point P about here, and I pretend to be a line here, my arms, then my arms don't touch the ground either on this side or on that side. And it's the only line that doesn't touch one way or another. It's a unique parallel through this point to that line. Well, that's very plausible. The trouble is that if I wobble my parallel just a tiny bit, the meeting point will exist quite possibly in another galaxy. This is not something you have complete control over. You can't guarantee from experience that there isn't just a tiny little bit of a wobble, which might depend on how tall I am, perhaps. So what mathematicians did was say, well, okay, we won't assume it. Chuck it out from the elements and derive it instead as a theorem. So then you'd have all the results you want, but you wouldn't have made this assumption. You've used the earlier assumptions, but not the new one. A great many people tackle this. Ptolemy the astronomer tackles this. We're more interested today in the numerous Arabic and Islamic scholars who tackle this. Al-Ghahari in the, well, you can see the dates. Tabit ibn Qurra, who we'll mention a bit later. Ibn al-Haytham in the West, the man who taught us that we see by light coming into the eye, not by something going out and coming back. Al-Khayyami, Umar al-Khayyam, whose name is associated with a wonderful poem in English. It has a slight amount to do with a poem in Persian. And Nasruddin al-Tusi, with whom we will be most concerned today. An earlier edition of Euclid, which is actually in this building somewhere, is by Ishaq ibn Hunayn and was revised by Tabit. I mentioned Tabit. And there on this side, again, you see this strange figure, this iconic figure, which tells us that once again, this is Euclid 127. This is a problem. And Tabit spent quite some time trying to get round it and establish the parallel postulate as a theorem. We wouldn't say he succeeded. Okay, Nasruddin al-Tusi, our subject for the first half of this talk, was Persian. He was a polymath, recently described as one of the greatest scientists of medieval Islam. He's the author of 150 treatises on astronomy, mathematics, mineralogy, medicine, philosophy, theology. He's remembered for being the first person to make plane and spherical trigonometry into an independent subject, kind of extracted from the depths of the work of astronomers and made into an independent discipline. And he wrote the book that concerns us today, the treatise that removes the doubt concerning the theory of parallels. And here are some pages from the book on the right, this one. In the Rome edition of 1594, it's not exactly what he wrote, it's a revised edition. But what we can see, I think, is there's quite a bit of Arabic. There's a large bit of writing, larger letters, and that figure there, I've exaggerated it and put it over here. So you see the same iconic figure. The large letters mean we're stating a theorem, and it's going to be Euclid, book 1, proposition 27, and That's what he's investigating. Remember, he wants to derive this as a theorem. He doesn't want just to state it and use it. And there's another similar thing up at the top there. There's another proof of the existence of parallels. But down here, and again I'll enlarge it, this picture here tells us we're going to look at how he attempted to show that the postulate was, in fact, derivable as a theorem. So here's the big picture of it. I've taken the liberty of covering one of the lines in red. So his story is going to go like this. You've got a sloping line, that one. You've got a horizontal line, this one. And you've got a bunch of perpendiculars. That's to say, you drop lines from here, and they meet the horizontal line at right angles, each of them. And what he says is that if this angle here is less than that angle there, then the line carries on downwards. And so if that angle there is less than that angle there, then this perpendicular is less than that one. So each time you drop a perpendicular, you look at the angles. And if the angles are smaller on this side than on that side, the line just keeps going down. Okay? So here's another look at the picture. If A is less than B, then P1 is less in length than P. And if the angle there was less than the angle there, then P is less than P2. So you hope to have P2 is less than P, is less than P1, and so on down. And then what would happen if it wasn't? What would happen if you had a couple of equal angles up there instead of unequal angles? The symmetrical case. Well, you might readily come to believe that in that case you had a whole bunch of rectangles. After all, we've got an angle there because it's a perpendicular. We made it that way. That's a perpendicular. Now we've got equal angles. That's a perpendicular. And you might persuade yourself that that is also a perpendicular. In which case, mathematicians would say you're well on the way to establishing, you're talking about Euclidean geometry, and something has happened. That's just worth bearing in mind. Now I want to give you a quick trip through how he attempts the parallel postulate. This is a bunch of figures that go to show that he's doing quite a lot of work. And this one here, which I'll blow up in a minute, is to show you how he goes about it in more detail. So remember, he can draw on 27 propositions of Euclid and a few more of his own. So here's the diagram. And where are the lines we're talking about? This is, well, down here is the transversal, actually. And the lines we're interested in crossing are the horizontal, the sloping line. Transversal here is the horizontal line. We're interested in the sloping line and this red line. The angle between the red line and the horizontal is a right angle. The angle here is less than a right angle. So the parallel postulate would say that the red line and the sloping line must eventually meet. So that's the aim. We want to show that the red line, if continued far enough, will meet the sloping line. Okay? So he starts off down here and this point, and he drops a perpendicular to the horizontal line. And he gets himself a little triangle. And then using the results he's already got, he gets himself a congruent triangle here, same shape, same side, and just copies that, and he gets himself to this point, and he drops a perpendicular, and he knows that these lengths are equal because there's so many things that are congruent. So what's going to happen? He's going to take a step from here, where the horizontal line and the sloping line meet. First of all to there, then to there, then to there, and so on, until eventually he crosses beyond the red line. This is going to happen somehow, at some stage. Now look at this figure here, which has got a straight side, a bit of the horizontal, of the sloping line, and another perpendicular. What can the red line do? It can't hit this side here, because then you would have a right angle triangle. A right angle there, and a right angle there. Two right angles. Angle sum of greater than two right angles in this triangle, and Euclid's already proved you can't do that. Can it hit this side here? Can the red line hit this side here? No, again, you have a right angle triangle there, with another right angle there, and you can't have that. So the poor red line has no choice but to carry on upwards and eventually hit the sloping line, thus establishing the parallel postulate, in the opinion of Nasruddin. Well, nice. What has been accomplished, actually? What's he done? Nothing. Sorry to say, but nothing has been satisfactorily accomplished. The parallel postulate has not been derived from the rest of Euclid's elements. All of the proofs, in fact, that have been going on in this time and later, quite a lot later, beg the question, but often in very interesting and satisfactory ways. Some assume that if you have a straight line and you draw a curve parallel to, alongside it, draw a curve which is equidistant from the first one. So you draw a straight line, and now you draw another curve equidistant from it, like the second track of a railway line, that second line will be a straight line. Some assume that the angle sum of a triangle is two right angles. Nasruddin's mistake is a bit more subtle, and I'm going to keep it back for the end of the talk. So all of these things creep in, perhaps by mistake, perhaps unnoticed, perhaps deliberately, and vitiate the proofs that were offered. It doesn't mean they're not interesting. It's worth a little digression to say that once you get to the 17th century, something happens to geometry. It's reinterpreted so that it's not just about figures. It's about figures in space. These figures you're drawing are in a medium, right? And what you're talking about when you're talking about geometry is figures in that space. There is a background medium. And astronomers from Copernicus to Kepler to Newton pushed Euclid's elements, Apollonius's conics, and much else out onto the universe, right? Where it had always been the province of the trigonometricians, if you like, such as Nasruddin. And just as soon as space became infinite, just as soon as the celestial spheres disappeared, you could do this, okay? This recent research by Vincenzo de Risi on some Leibniz manuscripts shows that Leibniz went even further. He hinted that what's at stake in all of these studies about the truth of the parallel postulate is properties of straight lines. And the crucial observation he tried to pursue was that the properties of straight lines derive from the space that they are in, okay? So you start to wonder what actually is a straight line. It's been having a rather tough time in all of these theorems. He couldn't make this insight that the properties of and ideal definition of a straight line would depend on the space you are in, but he raised it as a question. Now we move to perhaps a more familiar figure to you, the second civilian professor of geometry here, John Wallis. And he originally was a cryptographer for the parliamentarians and later for the royal court, and he was part of a community of scholars that formed the Royal Society. He was largely self-taught in English algebra, and his appointment here was, I think, an almost thoroughly political one in the first instance. And he retained it until his death, which is quite a long time, and set about learning Euclid, partly to justify his appointment here as a civilian professor. And he became a very successful mathematician, known internationally for his brilliant guesswork, which is, of course, the kind of thing cryptographers do, right? So that's the kind of maths he was particularly good at. I'll mention just three things he did: the Arithmetica Infinitorum, which is a very important work on topics that later became part of the calculus. He wrote a treatise of algebra, which has a very contentious nationalist historical introduction, but it's very rich mathematically. And he has a famous formula among mathematicians for pi as an infinite product, the product of an infinite collection of numbers. And, as perhaps you can see, he gave a lecture one evening in Oxford, in fact, on July the 11th, 1663, on the fifth postulate of Euclid, known by various other names in various other editions, as the 11th postulate, the 13th postulate, and so on. And he, of course, states it obligingly for us here. This is the parallel postulate. That's what he is lecturing on. He wants to try and prove it. And I wasn't able to produce a slide which would be legible even in the front row, but what you can see here is his name, Nasruddin, and that Pocock, who is an eminent Orientalist and Arabist, produced the translation that Wallis is relying on. It's just possibly you can see this saying Nasruddin's demonstration, but you can see that diagram we talked about before when we talked about Nasruddin, the horizontal line, the sloping line, and the perpendicular. Okay? And here you see the proof that I talked through. That would be the red stubby line that has to go and meet this sloping line here. And you can see the first bit of the apparatus. I think of all those little triangles that decorate a sloping line as some kind of scaffolding, really, that enables to move lengths along. His proof is different, and it goes in 3 steps, and I want you to start by looking at the red line, the blue line, and the transversal, which is the horizontal line at the bottom. So just for a moment, concentrate on the red line, the blue line, and the horizontal line. We want to show that the red line and the blue line meet because the angle alpha and beta, we assume, are less than 2 right angles. That's what we want to assume. So stage 1 is to simply copy the angle alpha, but over here. You get a line, of course, B prime, making the angle alpha with the horizontal line. I haven't said that B prime is parallel or anything. No mention of parallelism, just that I've copied the angle. Well, now you ask a question. Does B prime meet the blue line? Well, you bet. We made sure it did because it passed through the point B. Okay, then says Wallace, take a small step to the left and copy that angle alpha again, but here. Does this new line, which I call B double prime, meet the blue line? Well, you look at the intersection point of B prime and the blue line. It's moved a little, obviously, when we sort of do this construction, but it can't have moved very far. It must still be on the blue line somewhere. So let's put it, say it's up there at C1. So this line, anyway, meets the blue line. And now we say, look, you've got a triangle here, and I can scale it up, says Wallace. I can take this length here, and I can multiply it by the right number to make it equal in length to this thing here. So I'm going to scale this little triangle until it has a vertex here and other vertex here. Now, scaling does not change the angles. So what happens to B prime, to B double prime here? Right? It's, as it were, copied going along B, because the angle alpha and the angle alpha are the same. So when we scale this, we put B double prime on B. What happens when we scale this to C1? Well, it lies on the blue line somewhere. The scale copy will be somewhere up there on the blue line. And it's on B double prime, C1. So the scaled up version must be somewhere on the scaled up copy of B double prime, which is the red line. So the scaled up triangle has the meeting point of the blue line and the red line. Scale up that triangle, and it fits exactly on the base that you see. It has a vertex somewhere up at the top where it's supposed to, according to the parallel postulate. And you seem to have a proof. But Wallace isn't a fool, even by, he's a very, very interesting person, in fact. And he asks himself after through the lecture, can you actually scale up figures? Is that allowed in Euclidean geometry? And he concludes that all he has shown is you can do one of 2 things. You can take the other assumptions of Euclid, which everybody's been doing, and you can chuck in the parallel postulate, and you get a bunch of theorems. Or you can take the same initial assumptions, not the parallel postulate, and chuck in the existence of scale copies, figures of the same shape with different sizes. And that will give you a bunch of theorems, the same bunch of theorems. Whether you go for assuming the parallel postulate or assuming that there are scale copies of different sizes, you get the same geometry. So each assumption implies the other, but neither has been proved without the other. Okay. So I like Wallace for that. I come back to the question of what is a straight line, the one that perhaps Leibniz worried about. Mathematicians have essentially 2 ways of generalizing it. You can say it's the straightest curve joining 2 points. You have some way of saying of a curve that its direction never changes. You can say it's the shortest curve between 2 points. Let's take these 2 points here and join them by a curve. The straightest one, the shortest one is the one you want. That would be called the straight line. And you can prove under certain restrictions that in fact these definitions will agree. And you can do this on very many surfaces, not just the plane. And what we call these things which are the straightest things you can get, the shortest things you can get, we call geodesics. And here's a bunch of them. All the longitudes on a sphere are geodesics. They all join the North Pole to the South Pole. Crucially, like all the geodesics on the sphere, they're cut out by a plane passing through the center of the sphere. Typically, you think of the equator as another geodesic. It passes through the centre of the sphere. The latitudes, on the other hand, the other circles going round, are not geodesics. They are equidistant from the equator, but they're not geodesics. Okay, so that's the situation there. So these are geodesics on the sphere. And this jolly creature is a spherical octahedron. Okay, it has 8 faces, of which I think probably this one is the clearest, cut out by the appropriate number of planes through the centre of the sphere. All the arcs you can see are geodesic. Now what about the angles? Let's go to this point here. There are 4 angles, and because all of these planes that are cutting out at right angles, all of these triangles are actually the same shape and the same size, so all of the angles are the same. So there's 4 of them here. They're all the same. They all must be right angles. So this curvilinear triangle made up of 3 geodesics on the sphere has an angle sum of 1 right angle, which we now call pi by 2. 1 right angle there, 1 right angle there, 1 right angle there. So it has an angle sum of 3 pi by 2, not pi or 2 right angles as in Euclidean geometry, but then this isn't a plane, it's a sphere, so that's not a problem. There is something nice though, and I couldn't resist putting it in. Each angle sum of a triangle in that picture exceeds pi by 2. The 8 excesses, 1 excess from each of the 8 triangles, the 8 excesses add up to 8 times pi by 2, or 4 pi, which is of course the area of a sphere taken here to be of radius 1. So each triangle, okay, has 1/8 of the area of that sphere. So by an independent argument, the area of that triangle, each triangle, is 4 pi divided by 8, or pi by 2. So the excess of that angle sum over pi is equal to the area of the triangle. The sum of the angles of the triangle have an excess over pi, which is equal to the area of the triangle. And that's actually true for any triangle on the sphere, but I won't take up your time to prove it. What it does mean is that you can't scale up triangles on the sphere. As they get bigger, their angles are going to get bigger. Okay. We don't study spherical geometry by carrying spheres around. We study spherical geometry by making maps on the plane. Whether you think you're making a map of the Earth on an ordnance survey map or whatever, you tend not to carry a balloon around with you. You tend to get a large piece of paper out. And so, of course, I stole this picture from the web, and it's come from a mathematical source. So it's actually a source that's more interested in mapping the plane, the equatorial plane, onto a sphere. So and then we'll run the picture backwards. So in the background here is a plane. It's cut the sphere in an equatorial plane. The centre of the sphere is there. And what our author was interested in is take a point on the plane, join it to the North Pole. Never mind it's called P infinity, just join it to the North Pole. This line will meet the sphere somewhere, and that's your correspondence between this point on the plane and a point on the sphere. It goes to that point on the plane, which you get by just drawing a straight line. If you had a point perhaps over here, still on the plane, where is its twin? Its twin is going the same way. You join from the North Pole to the point you're interested and push on until you hit the sphere down here. I want to run it in reverse. So I want you to imagine that we have the North Pole here, and I want to produce a picture of all of the sphere except actually the North Pole by just shining light from the North Pole. Okay, this ray of light hits that point there and carries on and hits that point on the plane. This ray of light hits the sphere here and has already hit the plane there. So in this way, we get a picture of the whole of the sphere except for the North Pole onto a very large piece of paper. Is it a completely accurate picture? Well, I don't think it's pretty clear I don't think it can be. Points down here near the South Pole are going to wind up near O. Okay, the points down here are joined by lines to the North Pole. They go here somewhere. There's going to be a little bit of shifting around of the lengths maybe, but not much. Points over here, however, near the North Pole, are going to cast very long shadows. So if you shine the light from the North Pole through somewhere here, you're going to wind up on this plane, all right, but a long way away. And these bits of the sphere are going to be greatly distorted. It's like when you walk home tonight and you're casting your street lights cast you a shadow in front of you. Right? The further away you are from that street light, the more stretched your shadow becomes. Okay. So somehow or other, there's a relationship between the points on the sphere and the points on the plane. And you can imagine that mathematicians can sit down, put some coordinates on everything, and come up with a formula. And that formula will tell you, for example, what lengths on this piece of paper correspond to on the sphere. So your piece of paper, your Ordnance Survey map, your map of all of Africa or whatever it might be, has lengths on it, which you measure with an ordinary ruler, and then there's a rule which tells you, oh, if it's 4 centimeters from here to here, it's 1,500 miles from there to there, or whatever. And this rule might well vary from point to point on the page, depending on whether you're talking about a very small region, in which case it does vary actually, but you don't care, or a very large region, in which case you will be told by the map makers how to convert your centimeters on the page to actual lengths on the sphere. There are many, many ways of doing this. This is another one. I put the light at the center of the sphere. Everything that's going to happen now is in this little plane through the center of the sphere. It contains the light source, and look what happens to the rays of light. They come out, they hit the sphere in something that lies in that plane, and that's what we call the geodesic, because the plane goes through the center. So these rays of light come out and they hit the ground plane, the grey plane here. So they lie, these rays of light, in this plane, and they lie in this plane. Well, a plane cuts a plane in a straight line, right? Nothing else it can do, right? It cuts it in a straight line. So that tells you that the geodesic, this bit of the geodesic here, has been mapped to a straight line. So geodesics are mapped to straight lines. And I do it again on the other side, the southern hemisphere. You can make a map of the southern hemisphere this way, or any hemisphere. Notice that again, the map is not at all bad near the South Pole. It's distorted, but not terrible. It's a dreadful distortion as you near the equator. And again, you can imagine that it is true. There is a simple formula for this. And again, it tells you if you have some lengths on the page, what do they correspond to on the sphere. Okay? There are lots and lots of maps, and I want to turn now to the topic of reconstructing from a picture what is the surface you're talking about. Okay? So here are, just for fun, a couple of maps of a well-known sphere, the Earth. On the left, it's an angle-preserving map. I think it's Mercator's projection. I don't think it's a fat lot of use anymore, but you tend to see it in frontispieces of nice old atlases. On the right, also not very often seen, is an area-preserving map. Up to a constant scale factor, the map on the right has countries showing their size, and it's correct relative to the other countries. So it's amusing to see that on these maps, it's pretty certain that Greenland is, after all, smaller than Australia. Africa is much bigger than it is on the angle-preserving map. Okay, there's quite some political fun to be had out of these things. If I now give you a rule and I say, at each point of one of these maps, how do I know if I take a little tiny step, 1 millimeter on the page, at one particular point, what is happening to the corresponding point on the sphere? What is the distance on the sphere between 2 points, 1 millimeter apart, there in Brazil? Well, let's say, let's say Rio. Okay. If the formula tells you that, then you're in with a good chance of saying, oh, wait a minute, I can do some sums, and I can say, this is a picture of a sphere. Okay. If you remember your 100 Years of Solitude, one of Garcia Gabriel Marquez's novels, one of the characters there is imprisoned for a time, and he works out from looking at books that the world is round like an orange. Okay, that's what he essentially must have done. So here's our orange. And I just want to remind you that if you try and draw Euclidean pictures on the sphere, you're not going to succeed, right? So if you try and draw squares, okay, you can imagine, this is the equator, you can imagine drawing, taking a step there, same length there and there, a right angle there and there, and drawing the top somehow. I've joined it by latitudes, which are not GD6, but they do meet the verticals at right angles. Well, look, they shrink as you go up towards the North Pole. Your lines that look like candidates of being parallel will in fact meet all lines, all GD6 do that on the sphere. And this is because the sphere is round. It has what mathematicians are called constant curvature, and curvature is a key word here I want you to remember for a bit. Okay, if it's constant positive curvature in the mathematical world, could there be constant negative curvature in the world? And here is a constant negative curvature beast. Again, I try to draw squares on it, and if you go from the very narrow bit down towards the fat bit, which is a hard edge, by the way, you can't continue it. If you do that, the squares all bunch up, and if you go this way, they actually stretch terribly. And it's called negative curvature because if you sit on it, it's like sitting on a horse. Right? Your legs go downwards, and the horse rises up behind you and in front. Okay, that makes it negative curvature. What makes it constant is a piece of mathematics, right, that I'm conceding from. You have to take a particular curve and spin it around an axis to get this shape. And it's because it's spun around an axis that it's not going to help us terribly later on in the talk. So remember curvature, and we come to the heroes of the story in some sense for the 19th century. János Bolyai in Hungary and Nikolai Ivanovich Lobachevsky in Kazan in Russia. Both very well remembered by their people at the time, although actually Bolyai's statue was forgotten about until I think 20 years ago. It sits somewhere on the border between Hungary and Romania, and people didn't go there. There were 5 civic worthies who had their busts on a mayoral building. He's one of them. So we have an idea of what he looked like, and this is a painting done for the University of Kazan over here. Their work is so similar, it's easier to talk about just one, and I'll take Lobachevsky. So again, this is a picture, and it's got some transversals in it. So the first thing I want you to see is the 3 black lines. There's a horizontal one, there's a black line at the right-hand end of the picture, and the black line coming out of the vertex A, coming out of this vertex, and going straight up at right angles. In Euclidean geometry, you would say that the 2 black lines going upwards are parallel to the horizontal one. Lobachevsky said, okay, let's investigate what happens if that's not true. If in fact there's a whole bunch of lines coming out of A, a whole bunch, like the green one, which do not meet this one. Of course, there's a whole bunch of lines coming out of A that do meet this vertical. This purple line here meets the vertical. And so they must be held apart. The bunch of lines that don't meet the vertical are held apart from the bunch of lines that do meet the vertical by 2 red lines. These 2 red lines he called the directed parallel to this line here. And they get closer and closer to this line here, but they never actually meet it. He did a lot of work, and the upshot of all of his work is that you can make a very convincing picture of a different geometry from Euclid's, one in which the parallel postulate is actually false. Right? Not just we don't know, but false. We didn't assume it, we assumed something else which is different from it. And you get a bunch of theorems. As noticed, you start with the idea of infinitely many parallels, or ultra-parallels he called them, to a given point that do not meet a given line. in this geometry, the angle sums of triangles is less than 2 right angles, less than pi, as we would say. And they gave a whole bunch of trigonometric formulae for their figures. So, you want to know what happens? It's a disaster. It's a complete disaster. Their work is not recognized in their lifetimes. It gets the somewhat grudging, private acceptance of Gauss. Now, Gauss is the greatest mathematician of his time, and he knew these people by correspondence. He knew Boyai's father as a fellow student, actually. And he does next to nothing to promote their work. So why this flop? Why does it not succeed in it today? Bolyai and Lobachevsky go to their graves with their work unacknowledged. Well, the mathematical argument would be something like, look, they assume something, then they deduce things from it. Well, if you assume something that's contradictory with other assumptions, you'll wind up in a mess. They just didn't go far enough. They didn't find the mess. If their assumption is nonsense, something will go wrong eventually. They just didn't look hard enough. And that was an argument. And I don't agree, actually. For a start, they have all these trigonometrical formulae, and some quite distinguished mathematicians in the 19th century thought, no, that's telling us that this is going to work out. It may not work out quite with the ideas organized in the way these guys presented it, but it'll work out. So why wasn't it accepted? Well, I think, frankly, and I think it was true also for mathematicians in the Arabic and Islamic world, like Tabit ibn Qurra and Nasruddin al-Tusi, it just challenges the basic belief about geometry. If you haven't come across this ever before, and you've been trained up in Euclidean geometry, you would think Bolyai and Lobachevsky were crazy. And actually, of the very few reviews that Lobachevsky's work got, one was by a fellow Russian mathematician, more integrated with mainland European mathematicians in Paris, a man called Ostrogradsky. And Ostrogradsky reviewed Lobachevsky's work and said it was so bad, he was barely fit to be a school teacher. So there you go. He was essentially trashed. Gauss's private acceptance of it tipped the balance after he died, because people read Gauss's papers after he died and they realized that Gauss had accepted this. Gauss thought it was okay. And there was a kind of collective, okay, I don't want to disagree with Gauss that went on. Just briefly, because I'm nearing the end of the talk, it's rescued, this geometry, and greatly extended by two people, and I promised a very brief hint of other things in the flyer. So Bernhard Riemann, who's the man who dominated mathematics in the middle of the 19th century, whose ideas are still alive and very, very well today, is one of them, and Henri Poincaré, who comes along in the next generation, is another such figure, and they both, in their time, spent work on this. So here's another map. Remember I said, I give you a rule, I give you a picture, I give you a rule for determining lengths in this picture, and this, I say this is a map of something, and I've got a rule for measuring length. Well, what's the something? You ought to be able to find out. Well, here's a picture. You can look at it actually either as a flat thing, in which case you've got lots of triangles, and they're bunching up, getting squashed as you go outwards. Right? If you, the way Richard Feynman talks about this in lectures on physics is you imagine this is a plate made of brass and it's cooling down as it goes outwards, and so everything in it shrinks. Another way is to think of this as the nose cone of a plane, something with that paraboloid shape. So the bit in the front is sort of seen face on, and the further back you go, the more oblique a view you get of these triangles. Now here's the rule. The rule says that all of these triangles, let's take the black triangles, all the black triangles are the same shape and size in the thing it's come from. All of the white triangles are the same shape and size in the thing it's come from, and they're all actually all the same shape and size. So you've got a whole bunch of triangles here which have come, in their real world, are same shape and size. It's just they look funny on the map. Well, that's okay, right? You didn't object when I showed you the equiareal projection of the globe, or the stereographic projection of the globe, where the angles were preserved by the map. You just say, okay, just funny pictures of the sphere we live on. Well, this is just a funny picture of something else. Okay. Now let's think about this. We take one of these triangles I seem to have landed on, this black one here. It's obviously a right angle triangle. There are 4 angles here that are going to be equal, and if there are 4 angles at a point, each one of them is a right angle. So there's a right angle triangle. All these triangles are now right angle triangles. We know that. Come over here to this vertex of the triangle. You see 3 angles coming together, 3 black, 3 white, and you have 6 triangles all together sharing and adding up to 2 pi. So each angle is 2 pi by 6 or pi by 3. And up there you have 7 black triangles, 7 white triangles, and you have 2 pi by 14 or pi by 7 for the 3rd angle of the triangle. So these triangles have angles of pi by 2, the right angle, angles of pi by 3, and angles of pi by 7. And you do a little sum, and indeed they add up to an angle sum of less than pi. So you start recognizing this is not a picture of Euclidean geometry. But if you look at that picture, remember that picture, the triangles go on forever. So it's an infinite picture. And also you can look at this picture and you can think, let's take the hypotenuse of that triangle. All of those hypotenuses are the same. Now I've kind of covered it with a whole bunch of rulers. And with a bit of trigonometry, I could use the other strides as well. And so I can measure things in this world, okay? And if it's infinite, I can tell you things about the length in this figure using, shall we say, the hypotenuse as a unit of length. Okay, so it turns out, and the clue is because the curvature is less than pi, and you have, it's a bit like that bugle-shaped world, but without the loop around it that you can make, that this is a world of constant negative curvature. Okay? So it's obviously 2-dimensional, so could it be a picture of 2-dimensional space, physical space? Well, it does give accurate pictures of angles, right? And it has a rule for length. So if you thought you lived in a world like this and you just talked to somebody else on the bus, nobody overhearing you would think you were mad. You'd be talking about whether your new car will fit in your old garage, right? Things like that. You would be taking a sharp right-hand turn when you get to the main road. All of that kind of stuff you could do in this world too. You can measure angles, you can talk about length, just as you can in Euclidean geometry. Of course, it's different geometry. So what is it a map of? Now this is the really tricky bit. It's not a map of a surface that I can produce in space. I can't now produce something from my bag over there and say, well, this is a chunk of it, and you just, I couldn't bring you the whole thing because it's infinite, and I can't fit an infinite thing in this room, but it's a chunk of it. That doesn't exist. There is something mathematically that corresponds to that picture. It just doesn't happen to exist in 3-dimensional Euclidean space. Nobody said it had to, okay? Naturally, you think it should. I can show you a sphere. It's a 2-dimensional thing in free space, okay? But I can't do the same with this one. If we lived in 5-dimensional Euclidean space, I could, but sorry, I don't have a COVID passport for 5-dimensional space. So it's the genius of Riemann to say, look, think what Gauss said about curvature. Gauss said about curvature that if I give you this rule for distance, telling you on some surface or other how far neighbouring points are, if I go a little step in this direction and a little step in a right angle direction, how big is the hypotenuse? If I have that rule, then I can tell you other things about the surface, like its curvature. And Riemann, who is a student of Gauss's in some sense, said, that means I've got a surface. It doesn't have to mean that I've got a surface in Euclidean 3 space. That's a separate question. And if you have a picture and some calculus-based rule for interpreting distances, you get what I'll call a geometric surface, but not one you can necessarily put into three-dimensional space. So let's just explore this bit a little bit longer because we're nearly at the end. What are the geodesics on this thing? What is the best thing you can do for a straight line? I've deliberately drawn clumsily here because actually this is a toy you can take home and play with yourself in a way. You just need to draw a disk, and then the geodesics on the surface are either the straight lines through the center of this disk or arcs of circles that meet the boundary at right angles. Okay, obviously I've got a pretty generous idea of a right angle in this picture, but it's freehand drawing. What you can see immediately is that through the point P, there's a great number of lines that don't get anywhere near the horizontal line. This is the kind of thing that Lobachevsky was talking about. A whole bunch of lines coming out of there. Obviously, some do meet it. And there will be an arc of a circle starting there and finishing up there. There will be an arc of a circle starting there and finishing up there, which hold these two kinds of lines apart. This is a Lobachevsky picture on this disk. It tells us we're doing the same thing that Lobachevsky was doing. So were these people unlucky who tried to prove the parallel postulate before? On this surface, the angled sum of a triangle is less than pi. There are many geodesics through a given point that do not meet a given line. And as a matter of fact, although I can't show you that so easily, the curve equidistant from a straight line or a geodesic on that disk is not a geodesic. So what was Nasruddin's error? Where did he go wrong? Remember, he just says if that angle is less than that angle, then this perpendicular one on that side is less than the red one. And you just carry on down. And then what must happen is that this horizontal line must meet, this sloping line, sorry, here, must meet this horizontal line. That would prove the parallel postulate. So where's he gone wrong? It looks very plausible, doesn't it? Well, it's related to the previous picture. What the previous picture shows you is that you can carry on down for a bit, say with this one, pass through P, get to there pretty much, would probably be your nearest point to the horizontal line, and then you start moving away again. Right? You get to the symmetrical case, but you don't actually find yourself carrying on down. Because indeed it is the symmetrical case, you wind up going away again. So the line does approach for a while, and then it gets to the nearest it ever will get to the horizontal line, and it flies away. That's the thing that he didn't really expect. For all of his other arguments and all the other clevernesses that he had, that's what he didn't expect. Now, I think that's a pretty difficult thing to spot. Okay? So this is his error. There's a green line, it comes on down, and then it starts swinging away again. And you see here, if you've got two equal angles there, this one is not a right angle. When I said you could perhaps believe I was being a little naughty, you might believe it, but you certainly haven't proved it. Okay, so that you can see there, this line is not, these four lines here do not make a rectangle. There might be a right angle there. There are two here and here, but that is not. Again, it's less than the right angle. So what you find is that Nasruddin's error was to assume that if one line is descending towards another, like an aeroplane coming into land, it then swings away again. Okay, I promised in the flyer a very brief mention, a really scandalously brief mention, as it turns out, of the connection here. Einstein's ideas about special relativity were partially shaped in a reading group, a book group. Those of you who've got book groups going on might want to be inspired at this point by studying Poincaré's popular essays. The maths was then put into geometrical form by Hermann Minkowski. Einstein didn't like it much. And then he started working on gravitation, and he realized he needed very hard mathematics from Riemann. And that he learned by working with his friend Marcel Grossmann in Zurich, who was an expert on Riemann's ideas. And they decided that the curvature of space-time, that's Minkowski's introduction to space-time, the curvature of space-time is going to be what captures gravity. Okay, so it's not a force, gravity in this picture of the world. Curvature is a picture of the world. Okay, so that's where these things have come together at some time at the start of the last century. So a few conclusions. The very beautiful books which you see there show there's been a long-running concern about Euclid's axioms about parallel lines. There's been a series of mathematicians attempting to turn that parallel postulate into a theorem, notably Nasruddin and Tusi. And I realised giving this talk I forgot to give you enough biography about some of these people, so if you want to ask, I'll try and answer questions about that too. All they did was discover assumptions that are equivalent to assuming the parallel postulate. Bodleian and Lobachevsky have the courage to first people to describe what a non-Euclidean geometry might be like. And Riemann and Poincaré give it rigorous foundations and indeed a wholly new approach to geometry. Credit, by the way, should go to Euclid for one thing. He assumed the parallel postulate. Euclid is not one of the people who tried to prove it. It's just an assumption with him. We don't know why, I admit, but it's just an assumption with him. And when we have a succession of mathematicians in the Islamic world who identify this problem, they care very much about it, a very critical, serious bunch of mathematicians. They make vigorous attempts to rectify it. And many of their failures, if you like, their blunders, turn out to be theorems in non-Euclidean geometry. You can rescue them in the new setting as theorems. Thank you very much.
Will you take some questions?
Yes, cool. Yes, Mike.
Why do you think that spherical geometry was failed to be early on to be put in the same context as Euclidean geometry?
I think because it's finite. That they're not actually at this stage trying to say what, and well, put it this way. They want their axiom system, if they want to axiomatize it, as formal as they can be, also to be that axiom system which applies to space. Now, in this geometry, you can prove, without any reference to parallels, that you can't extend lines indefinitely. And you can see it on the sphere, of course, because they just join up themselves. So that's a provable theorem in Euclidean geometry before you get to parallels. And so it says that if you also want this geometry to be a geometry of space in any way, then nobody believes, well, nobody then believed that space was finite, right? So it's out of the window straight away. It doesn't mean it's wrong, right? But it differs from Euclid in two respects: the parallel postulate, obviously, and also its finitude. And they just didn't want to have that as other than an entirely separate geometry that doesn't bear on the question of the parallel postulate or the nature of space. So that would be my answer. I've crushed you all. Math panic set in early on in the talk. Yes?
Could you please tell us a little bit more about Bodleian and Lobachevsky? Are they collaborating?
No. They find out about each other's work about 10 years after they've done it. So Bodleian's father attended Göttingen University at the same time as Gauss was a student, and tells us that it was they became friends. He said it was absolutely terrifying going on walks with him, because he would say something mathematical that was wrong and he would just look at you as if you were just stupid. So he didn't learn anything from Gauss really, except that the guy was very smart. And he carried on trying to prove the parallel postulate when he went back to Hungary. And his son took up the course, that's János. And János was quite liked by the students. When his father was ill, János would step in although he's probably about 15 at the time. But they thought Janos was a clearer lecturer than his father. And when Janos takes up non-Euclidean geometry as a pursuit, can it be? His father writes to him and begs him not to do it. The wonderful letter where he says, I've sailed past every reef of this infernal sea, and each time returned with shattered mast and torn sails. It's the Romantic era. So he doesn't want his son to do this. His son carries on, and they do the two-dimensional case. They get worried about the three-dimensional case and hold off for a bit. And eventually they decide to publish. By this time, the father has written a long 2-volume book in Latin on geometry. And so they pop Janos's discovery in as an appendix, a 28-page appendix, at the back of this unreadable book. They send a copy to Gauss, it gets lost. They send another copy to Gauss. Gauss replies to say that it's very impressive, but I know all this already. And Janos refuses to publish ever again. He thinks, you go to the top guys and they lie. What's the point? He can't have known this. Gauss did know the two-dimensional case. He did not know, in my opinion, the three-dimensional case. Lobachevsky, quite independently, at the same time as doing this work, he had a maths teacher called Martin Bartels, who was known as the best mathematician in Germany before he went to Russia. And so people would say, what do you mean, there's Gauss? And the reply would come back, Gauss is the best mathematician in the world. This is just the best mathematician in Germany. But he doesn't seem to have talked to Lobachevsky about this stuff. And Lobachevsky starts in, has an idea that parallel postulate is true, gives a lecture on it, realizes he's gone wrong. Then he has to accommodate himself to a rather nasty period of repression in Russia. A man is sent out from Moscow called Magnitsky to impose orthodoxy on the provinces. This lasts for a while. And then he goes, and Lobachevsky starts publishing at great length in Russian, only turned into German at the end of the 19th century, in which he does everything like this. He then publishes an unreadable article in French in a mainstream journal in Germany, a booklet, which is in German, and at the end of his life, another attempt. And I think it's the books, actually, the Russian books, that Ostrogradsky says are barely worthy of a school teacher. So that's him. He becomes rector of Kazan University for a long time, steers it through a cholera epidemic, rescues it from financial crises, establishes a library and an astronomical observatory, and I think right at the end of his life gets dementia. So they're completely independent. They find out about each other in the 1840s, and they're quite pleased that somebody else has done it. But they must be giving up hope by this time that anybody outside their immediate circle thinks they've done anything at all. So that's who they are. And I should have said about, for example, if I may take this moment, Nadarina Tusi was around at the time when there was a great threat to Persia from Genghis Khan. So he has to move from place to place to place as the Khanate expands, and he winds up working as an astronomer under the rule of Hulagu Khan, the son. Doesn't seem to have stopped him grinding out 150 treatises all the same. So I think he's really rather an impressive character. Yes?
Recently I was checking some essays on theory of knowledge, and the question was, does mathematics and another area of knowledge produce knowledge that is independent of culture? So you've compared sort of types of thinking in various cultures. Do you think that mathematics produces knowledge that is independent of culture?
It's a very hard question, actually. I mean, obviously, in some sense, 2 plus 2 is 4. And if the Zorgians turn up, 2 plus 2 is 4 for them too. So I would expect that if they turn up and they say, wait a minute, we didn't ever get non-Euclidean geometry, that Nigel and Martin take them aside and they would go, oh, okay, fine, we get it. which is to say that there are different priorities. There are different ways of getting these results. There are different ways of organizing these results. In a way, this is a story about a definition of what is a straight line. And that's also something we don't get until the 1960s. I think this question is very good. And the things we all consider to be a straight line is really to say that it is a geodesic in the space of zero curvature. Well, I mean, there are many definitions. And definitions from other branches of geometry. Some of them very strange, because the geometries are very strange. So, I think the theorems in the end are transcultural. They go from one culture to another with some work. The starting point, well, mathematicians, I've heard say that as they do their work and they refine it, one of the hardest things to do is to get the definitions right. You want the definitions to somehow be deep enough to capture something, but easy enough to work with. So I can imagine cultures doing that differently. There are times when drawing figures in mathematics is acceptable, and times when it's simply not. Lagrange was very happy to do analytical mechanics, applied mathematics at the time, with no figures at all. All right? I don't think you would explain to somebody how to get a satellite to Saturn with no figures at all. So and obviously there are incompatible theorems, right? When I was teaching at the Open University and I met students, I would say, I'm a non-Euclidean. I think space is non-Euclidean. I don't think it's Euclidean, right? I'm back to loser, I think. I'm just really probably made a bet on round here near the sun. It's a little bit positive curvature-ish, and gets a bit more positive curvature-ish as you go in towards the sun. But I thought, give them a fright. They ought to meet someone who thinks that space might be something else, and you could genuinely believe it. Well, obviously for such a culture, right, they have those theorems as the bedrock theorem, and they regard Euclidean geometry as rather straightforward, special case somehow or other. But I think each culture would have to agree with the other. And what Poincaré says, of course, is if you met Poincaré has a lovely argument. He says, how do you know whether space is Euclidean or not? You can't tell. Because what would you do? Right? You'd have to build a triangle, a really big triangle, and measure the angles in it very carefully. So you might do it with chains, or you might go into space and do it with light rays or whatever, and you measure the angle. Now let's say the angle of that triangle is less than pi. Does that mean space is non-Euclidean? No, it might mean that you haven't used straight lines after all. Your light rays aren't straight. So you have a choice. And how do you make that choice? It's whatever's more convenient for you. There's no other way than saying, oh, come on. Then he had a very strange argument for why choosing Euclidean geometry would be the most convenient, by the way. But he's right. If you take a mathematical theorem and you say, I will incarnate it in these things, and I will say, these physical objects are straight, it's open to you to say, no, they're not. They're subtly curved. And the question is whether you think that's making life easier for you or not. When you come to general relativity, this argument is very, very hard to maintain. In fact, I would say it's impossible to maintain. But that's a whole other story. Okay. But that would say, for your example, that you could imagine a culture which felt that some theorems were fundamental, and another culture that thought they were, let's say, special cases. These aren't the ones that apply, or whatever, right? I mean, it's possible somewhere in the universe there was a planet where people way early decided the world was round, and have always cared about spherical geometry. flat geometry, you know, it's a funny little subject. Actually, the opposite, of course, of what we've done. So, the approaches, the methods could be different. The definitions and their place in the theory could be different. The actual theorems, the actual results, I don't think so. No. No.
Are there any further questions? In which case, thank you so much for such a fabulous lecture. I really learned that I know nothing, which is important as a starting point, as a non-mathematician, and you know.
Know something now.
But I did see that there's a whole world of understanding of mathematics through subtleties. I think a subtle detail can make a huge, enormous difference in the history of maths, and that's one thing I've understood. So thank you for that. I'm indebted.